All right, let's pick up with orthogonal sets. What this is we're given a set of vectors, and we're just asked a very simple question. Does this set qualify as being orthogonal? And what we want to know is, are every pair of vectors at a 90-degree angle to each other? And there's not one move that does this. We've got to check each individual pair. So I've labeled these vectors u, 1, 2, and 3, and so here we go. How do we check if a pair of vectors is orthogonal? We check the dot product. So here we go. u1 with u2, multiplying across, that would be 0 plus 3 plus negative 3, check. 1 with 3, negative 10, positive 9, positive 1, check. And finally 2 to 3, 0, positive 3, and negative 3. Yeah, so every pair of vectors is orthogonal. And we checked all three, so this, yes, is an orthogonal set. Here's another example. So I just three vectors. I can be in any R space, and in this case, again, I have to check every possible pair. If there was a fourth vector, we'd have, looks like we'd have to there'd be, I think, 6 different pairs we'd have to check, but I don't think we're going to run into that in our homework. So here we go, 1 to 2. So negative 20, minus 4, plus 0, plus 24. So far, so good. 1 to 3, we've got 15, minus 12, 0, negative 3. We're on a roll. And finally, the last pair, 2 to 3, we've got negative 12, positive 3, minus 12, and minus 8. Ugh, not 0. So we were almost there. The first and second are orthogonal, the first and third are orthogonal, but 2 and 3 are not. So this is not an orthogonal set. All right, example 3, two-parter. First thing I want to show is that we've got a set. I want to know is not only is this an orthogonal set, but is it a basis for R3? And so this is a little more restrictive. For instance, these two examples up here, this was a basis for R3. This was not a basis for R4. I would have to have had a fourth vector. So back up to this orthogonal basis. What do I need? First of all, we're going to check, are they orthogonal? I might just kind of point and call out numbers here. 10, minus 10, 0, check. The first and third would be positive 5, minus 5, plus 0, check. And then finally the 2 and 3 would be 2, plus 2 is 4, minus 4, check. So yes, orthogonal. And is it a basis for R3? Yes. So we checked orthogonality. Boom. And what makes it a basis? I need 3 vectors. Check. And they are all independent. And the way I know that is if 2 vectors are at a 90-degree angle, they are clearly heading in different directions, so they are independent. So we're good there. So here comes a very classic question for our class. Can you express this target vector then as a linear combination of those 3? And this goes back to our early days. I could put this in a augmented matrix, row reduce, and we would have it. But there's something powerful about having an orthogonal basis. And I'm going to show you that all we're looking for are my scalars. What would I have to scale each of those by, then add to come up with this target vector? And there is a way to find the scalars without having to put it into a matrix. So if I let C represent a generic scalar, what we do is we take my target vector and dot it with each vector separately. So what this looks like in general, you're going to take the target vector, dot it with the first basis vector, I'll just call it u in general, and divide that by the basis vector dotted with itself. So that's the generic look for how we're going to get each of the three scalars. So here we go. Here's my first one, C1. So x dotted with u1 would be, let's just do this in our head. So 5 times 5, 25. Negative 2 times negative 5, that's positive 10. So 25 plus 10 plus 0. So we've got 35 over u1 dotted with itself. So 25 plus 25 plus 0. Boom. So there's my first scalar. We can reduce that, clean it up. Let's go ahead and do that. That would be dividing both by 5. We've got 7/10. My second scalar. Again, I start with my target vector and scale it with the second basis vector. So positive 10 minus 4 is 6 minus 1, so that's 5. And then my basis vector dotted with itself, 2 times 2 plus 2 times 2 plus negative 1 times negative 1, 4 plus 4 plus 1, 9. Don't need to reduce. Last round. My target vector dotted with my last basis vector, so 5 minus 2 plus 4 is 7. And then u dotted with itself, 1 squared plus 1 squared plus 4 squared is 18. And that's it. What a powerful way to get the linear combination of these orthogonal vectors. And that's the secret here. It's not something we've kept all along. We usually have linear, we have independent vectors, but not necessarily orthogonal. Because of orthogonality, that allows us to use this workaround to get those the scalars. So again, if I had 7/10 times u1, 5/9 times u2, 7/18 times u3, that linear combination would give me my target. Just as a quick follow-up to that, I just want to show you what we've normally done with this. Let me head to my matrix. I've already entered the data in here. You'll see there's my here's my basis vectors, u1, u2, u, and 3, and I'll have in my fourth column there's my target vector 5, negative 2, 1. So already entered. Let's head back to the home screen and let's get RREF of matrix 1. Boom. There's the decimal form. If I hit math, fraction, how's that? There's the same scalars that we calculated by hand using our old technique of row reduction. Love it. All right, well that takes us to our last example. Orthogonality. Here is a visual picture of what's kind of going on. I'm going to show you a technique, and I'm going to have to skip past some of the development of this, but I just want you to see in general. Our goal here is to project a vector, let's say 7, 6, onto a vector u, 4, 2. And I want to project it orthogonally, meaning if I could project this in a certain direction, I want to land on this vector here. Well, orthogonally means at a 90-degree angle. And so the first concern is this u vector, we need to scale it so it has a place to hit. And that's the first step in this process. I don't know if you can see on the video, but I very lightly have scaled a dashed line so that u has a place to land. And so how do I scale this down? Well, we can see we're gonna hit somewhere around here, and we're gonna call this new spot, the scaled version of u, I'm gonna call that y hat. And what we need is y hat is just a scaled version of my u vector. Well, how do I get this scaled? How do I get this scalar? Well, like that last example, all I need to do is I'm going to take my this target vector, and we're going to project it onto this basis vector. In the same way we did before, what would that look like? It would be y dotted with u over u dotted with itself. So let's get there. All right, so that gives me y dotted with u, so that's 28 plus 12, 40. And then u dotted with itself, 4 squared, 16, plus 2 squared, 4 is 20. Nice. So my scalar is 2, so I'm going to come back over here and say my now scaled u, which I call y hat, is just 2 times my basis vector, 4, 2, which tells me that lands at 8, 4. So if I go back to my graph and figure out where's 8, 4, 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, that is the perfect 90-degree projection onto my u vector. But again, we're going to call that y hat. That's at 8, 4. And then finally, so we did it. And so the last thing we're going to do is we're going to, we now, in a sense, have a orthogonal basis. We have the u vector, and I need to figure out this guy right here. And how do I figure out the vector in between these two? Is we just subtract y bar minus y hat. And we're going to call that the z vector down here. So let me come down. Say if I take my original target vector minus my new scaled one, we're going to get this orthogonal vector. So what was my y bar? 7, 6. My scaled u vector was 8, 4. Subtracting gives me negative 1, 2. So negative 1, 2 is the orthogonal vector coming off of my u vector. Well, negative 1, 2 is, it's like this little piece right here shifted down to the origin. Negative 1, 2 looks like this. And that's my z vector. Whoops, got those backwards. Negative 1, 2. Okay, so put it all together. I've got 4 vectors all floating around. What was my original goal? Was to project 7, 6 onto 4, 2. I first had to scale it out. We projected it down, and now this little piece right here, that z vector, completes the orthogonal connection. So starting with u as a basis, what we could also do is there a way to think of an orthogonal combination of vectors that gives me my original 7, 6, and we've got it. I want you to see this. So my y hat, my target vector, is just a combination of that y hat plus my z. And let's check that out. What that's saying is my target vector, 7, 6, is just the sum of my scaled basis vector added to my orthogonal vector, and it does, it checks out. What's so special about this is just, again, it's just a linear combination of these two that adds back to my target vector. What's so neat about these two is they are orthogonal, and you can check it quickly by inspection with the dot product, 8 times negative 1 plus 4 times 2, and we're good.